my work is, as said, introduced, is focused on using game theory and AI to model mixed traffic, especially accounting for emerging technologies such as autonomous driving. So first, let me introduce the research we have been doing in my lab for the DitecT. And so of course, we focus on transportation, especially leveraging data and innovative technology. But we also try to collaborate with people outside engineering school. So for example, I have an ongoing project with 6 other PIs to work on how we can better manage subway crowds during the COVID pandemics and afterwards. So we use the agent-based simulation, also virtual reality, to model how the agents behave and interact with each other, how that have the implication for health, public health. So we also had work using 2,000 drivers, 5-year driving data, trying to understand whether they can provide some biomarkers for early detection of dementia. So our recent work, including using physics-informed machine learning for traffic state estimation. For example, we can learn fundamental diagram using the data. And then my research interest also heavily shifted to generative AI. For example, we use the diffusion models to generate videos, driving videos in critical driving scenarios. For example, we start from the top video, but then we can replace the background by rain, fog, even from urban to rural areas to generate more corner cases for to train robust driving algorithms. But all these center around so-called digital twin. Here we call it hybrid twin. So because hybrid means we leverage both the data and also the machine, as well as the domain knowledge. So the one digital twin we are trying to develop now is based on a real-world testbed called Cosmos. So Cosmos testbed is a testbed that is established to test all kinds of mobile wireless communication technology in urban setting. We had different sensors, including cameras and cloud edge computing, to extract the object detection and also the tracking from the video and convert them to so-called MQTT messages, which are a standard protocol used for IoT device messages these days. So many people may think, okay, that's the digital twin, but I think these are just the eyes of the digital twin. So the camera, the computer vision can help us better see how traffic moves, how cars and pedestrians interact at intersections, but that's not the whole key in this development of digital twin. So as a traffic engineering researcher, we should be able to think about how we can leverage this data to predict and simulate the traffic condition better, using no matter the open source traffic simulator that nowadays used widely, including Sumo or Kala, as well as virtual reality building on, say, Unreal Engine. And then by simulating these future traffic conditions, the key is to control them and feed back to the real world. And then all these require AI algorithm because it involves large amounts of multi-modal data sets. To close the loop in the digital twin, so my group focuses on 3 pillar methodologies: game theory, control, and machine learning. So we believe that these 3 fields actually interact with one another. For example, game theory, how to nowadays trying to marry the learning community when the environment that where players play for games is uncertain or unknown. And also within the control setting, if the plant or the control environment is unknown, so machine learning have to also be used for learning-based control. And today I will talk about how we merge these three fields together for autonomous control. And the research question we try to address is we are not only interested in control one autonomous vehicle, but a large number of autonomous vehicles in human traffic streams. Let me first review what's out there. So the large number of autonomous vehicles, we can treat them as the agents. And multi-agent system is very common in both the social world and also the natural world. And the people from different fields try to tackle this network multi-agent systems, including the network of cars and the passengers, how we can match them together in ride-sharing platform, and also the network of large neurons. And each neuron can be treated as an intelligent agent, and how they interact and make decisions. And also, if you look at they fly characterize these patterns. There are several categories of methods that people use to model mixed traffic. Normally, when we model, say, a human-driven car follows another car, our goal is to train a driving controller F, parameterized by some parameter theta. And then there's some feature input and output, which is the driving acceleration. In existing literature, people use, say, adaptive cruise control, assuming all these cars in a platoon of, now I'm talking about autonomous cars, they collaborate with each other. Or people develop nonlinear carpooling models that can characterize also autonomous vehicles. So some use optimal control problem because they assume autonomous vehicle have some objective function they try to optimize, or model predictive control so that the autonomous vehicle can project the future based on the future prediction and update their current actions. However, what's the difference between autonomous vehicle and human-driven vehicle in this setting? So there are several different aspects. The reaction time. So the autonomous vehicle assumed have shorter reaction time, and they may have global information because they have more powerful sensor, including LiDAR and more cameras. And the driving control for human vehicle probably is heterogeneous, but for autonomous vehicle could be more homogeneous because they can be controlled by the company or by the software engineers. So this is the first type of methodology people use to model the mixed traffic and how they distinguish between the human driver and autonomous cars. However, this method may suffer when the driving environment is uncertain. When there are more and more cars in the background, that it's hard to model how they behave. That's why in recent years, we see many researchers shift to these learning methods, including reinforcement learning and imitation learning. So the essence of reinforcement learning is that we have state action space, and also we know the transition probability of the environment. And also we know the reward that each agent have to optimize. So the goal is to solve an optimal policy path. And on the other hand, imitation learning is we assume we don't know what's the underlying reward that expert trying to optimize, but we observe their sampled trajectories. So then we have some experts who's driving their car and we observe how they drive. And then our goal is to also find optimal policy, assuming we don't know their underlying reward. And so existing algorithms to solve reinforcement learning, including model-based and also model-free methods, and especially the A2C, which is the actor to critique, and the PPO now recent years are shown to be very powerful and robust in controlling self-driving cars using reinforcement learning. And for imitation learning, we need a large number of expert trajectories, demonstrating trajectories. So the algorithm, including behavior cloning, basically is a supervised learning. We observe the state action pairs and also transition, then we try to learn that the mapping. And also the inverse reinforcement learning is become more popular these days. Or in other literature, it's called apprentice learning. Basically, it leverages game theory to learn the underlying reward first and then infer the action. And also adversarial imitation learning, such as GIL, which is a generative adversarial imitation learning, turns out to be also a powerful tool. So for these methods, there's also pros and cons. For example, for imitation learning, if the expert data is not sufficient, so then the autonomous vehicle may not be able to learn the right behavior. And also most methods are built on single agent environment. There are more and more papers on multi-agent reinforcement learning and imitation learning for autonomous driving. There are also more established algorithms, but there's always some pros and cons in that aspect. So that's why in this study, our solution is mean field game. So it's more like a formal method that trying to characterize how the behavior evolves if every car is an autonomous vehicle. So in this talk, I will first introduce how we model, how we apply mean field game to multi-vehicle control on a single road. Then we will extend it to network that also involves how cars have to choose the routing behavior. And then I will generalize to the mixed traffic signal. And in the end, we will also talk about how we apply learning algorithm to solve this mean field game, and also some open questions. And so mean field game is actually a decision-making model for multi-agent systems, especially the model sequential decision choices of each agent. And normally a game is a non-collaborative Nash game. If people want to study collaborative games, so there's also the mean field control models out there. And why it's called mean field? Because it has to solve this n player limit to let the number of players go to infinity. So since it's introduced back in 2006 and 2007, it has been able to explain many behavior we observed in both the social world and also the nature. How do we apply this to self-driving cars? Because this game actually is very unique in the sense that it merged the microscopic agent level and the macroscopic mass population behavior. So that can really help us to translate from individual cars driving behavior to the general population behavior. So to describe how we apply this, I will start with the n-car differential game. So assume all these cars are running on a single circular road, and we focus on that green car n. Its position denoted by xn and the velocity is vn. Assume this car is trying to solve an optimal control problem, so it has an objective function. So fn here, because it's within the integral, so it's a function of, it's time dependent. We call it a cost function. You can specify any objective you want here. For example, the car has to minimize its running cost to avoid the congestion, to be safe, and also reduce the emission. And the big V at time t is the terminal cost. This is some cost we want to specify this car n to achieve at the end of the planning horizon time big T. And the goal for this green car is to solve optimal velocity control V. star. And then we can define a Nash equilibrium because every car also trying to solve this optimal control. So the Nash equilibrium is interpreted as when other cars fix their driving strategy at v minus n, so this car has to minimize this objective function j. And so to solve optimal control for two cars is fine, but if we have more cars, then this problem is not easy to solve given the dimension of the problem, and also all these optimal control problems actually couple with one another. That's why we propose this mean field game that can control many cars, and also somehow it's connect. We found a link between the new traffic flow theory and the mean field game. So now let me explain how we apply this mean field approximation. So mean field approximation requires us to take a limit as the number of cars big N go to infinity. Then the cost is also changed to the f cost function not only depends on the current car's velocity control as well as traffic density rho. And for the green car, we don't observe like each car's index anymore because they are all homogeneous and indistinguishable. So we call green car a representative car, agent. And then we remove its index. So this car also doesn't observe each individual car in its neighborhood. Instead, it's only observe the traffic density. Then we can have a mean field equilibrium. It's characterized by two fields. One is the uxt, which is the velocity field at time t and location x, and rho xt, which is the traffic density at time t and location x. So mean field game normally is characterized by two PDEs. The first is called agent dynamic, and it's formulated by so-called HJB equation. So basically, the V here is the optimal value that this car have to solve. It depends on the function f. And to solve this optimal control problem, so we can use Pontryagin theorem, and then we can solve that using the basic dynamic programming, etc. And here, the f is a function of the control itself, alpha that we want to optimize, also traffic density rho. So once this HJB equation is solved, assuming we know traffic density rho, then we can output an optimal velocity field, which is uxt, to another partial differential equation, which is the FPK equation. So rho here is the traffic density, u is the traffic velocity. So rho t plus rho ux equal to 0. This is the common conservation equation people normally use to model, say, fluid dynamics or other dynamics, as long as the quantity is conserved. And then once we solve FPK, then it can give feedback the rho, which is the traffic density field. Then this process goes back and forth until it converges. Then it gave us the mean field equilibrium. So I will skip the algorithm here. I will come back to that later in the later part of my talk. But let me show you just an example how the control can makes a difference. So LWR is a common first order traffic flow model people use based on partial differential equation. Its formulation is here. Basically, rho is the traffic density. Big U of rho is so-called fundamental diagram. So basically, rho normally we use Green-Shield fundamental ground. It describes a functional form between traffic density rho and also the speed U here. So UM and ρm are the parameters. Normally they are constants. It means the maximum density and maximum velocity. And for LWR, we first remember to solve Mean-field gain, we need an objective function. And we found LWR can also correspond, even it's a partial differential equation, it corresponds to some objective function that can be solved in the context of mean-field gain. So here, I remind you again, UQ is the fundamental diagram describing so-called equilibrium speed given traffic density rho, and UM is the maximum speed. Normally, it can be used as the speed limit. So inspired by this cost function, we design another mean-field gain using this cost function, but add another term here, the blue term. So the rho is the traffic density, ρm is the max density. And this term means that we not only ask car to drive towards the equilibrium speed, but they have to also avoid the high density area. And let me show you an animation and see how these two different control can make a difference in the final traffic behavior. So the lower chart describes how the blue line is the traffic density, the red dashed line is the traffic speed. So the x-axis is the space because it's a ring road. So we just unfold the ring road and assume at the point where we unfold it is one is marked as 0 and 1, but they share the same condition. So that's why we have periodic boundary condition. The left-hand side shows how mean-field control evolves, the mean-field gain evolves the density and velocity. The right-hand side, the LWR model. Let me start the animation. So you can see the in both scenarios, cars at the same location and the same condition, but as time goes on, we see a steep shock under LWR control, but the mean-field gain actually gradually smooths out the traffic. You just keep playing. So yes, we can see by adding this additional term to avoid the crowds, actually mean-field gain control try to steer the traffic towards uniform flow where on the LWR, so this shock wave forms. And so this tells us the fast is slow because to interpret this scenario, so when this yellow car see there's some high density in front of it on this ring road, for mean-field gain, the yellow car will tend to slow down. But for the LWR model, because it only depends on the local density, so it will drive fast in the low density area and immediately decelerate when it hits this interface, when the traffic transit from the low to high density area. So that's the interpretation of the mean-field gain. So under mean-field gain, agents have some anticipation ability. They can anticipate what the traffic would behave in the future so that they can adjust their control much earlier. So any questions for this part? Before I move on to the next part, which is the mean-field gain on networks. Feel free to interrupt me while I'm talking, or feel free to leave your question also in the chat box. Okay, maybe let me move on.
Yeah.
So
Yeah, sorry, I just wanted to say I don't see any questions. You can also write in the chat box if you have any question in the middle.
Yeah, thank you. So the part 2, we try to model how multiple vehicles interact on networks. Because when self-driving car navigate a network, they not only have to decide how fast they drive on link segment, but also at the junction point, they have to decide which routes they want to take. And if there are more cars in a space, so a game forms. For example, Waymo trying to like expand its robot taxi service in San Francisco and in also Arizona, and also now it will start also in New York City. So the multi self-driving car control on networks would be critical in this aspect. So how do we model AV on a network? So when they move from node K to I, so they can follow the mean field gain I introduced in the first part. But when they reach node I, they face a decision which route they want to take, IR or IJ. So to model this, we introduce some additional control variables. The first is beta. It means the percentage of all the probability this car, green car, will select the IR or IJ at time t when it's at the node I. So that's the meaning of this beta. And it had to be associated with this destination node D here. And this is a mixed strategy because beta can be a fraction number between 0 and 1. But if it's greater than 0, which means the link IJ has a probability of being selected. And based on this variable, we can also characterize its optimality condition by introducing the pi. Pi is the optimal cost. I will come back to this later. But if beta is 0, which means this link IJ is not selected, then this equation will become inequality. So what is pi? Pi is the optimal cost at node I with respect to its destination node D. So sometimes we also call it the potential between node I to D. Its physical meaning is it's the minimum cost this car can generate if it how to make a decision of route choice at node I. And pi JD is similar. It's the optimal cost from J to node J to D. And CIJ, so tau is the travel time when the car have to traverse from node I to J. The CIJ is the minimum cost that depends on some objective function we stabulate to this car. We can use any cost function that we introduced in the first part. So that's why, based on the optimality condition, if beta is greater than 0, so this have to hold in equation because pi ID, it's the minimum cost from I to D should be the minimum cost of traversing IJ plus the minimum cost from J to D. If we have more cars, so this green car can have to also queue up and node I, so then it incurs some queuing cost. But I will skip here for the to save time. So let me just show. I will skip many details how we model this mean field gain on network. Let me just present a simple two example to demonstrate the effect. So we have this simple network with 4 nodes and 5 links. Assume the cars are coming from node 1 and 2, and they all end at node 4. 4 is the destination node. And then the object function we select include the running cost and the queuing delay. And so I will also compare if the cars are controlled under LWR versus the mean field gain, how the traffic pattern evolve differently. So rho is the traffic density, so U is the travel velocity. Let me introduce the x and y axis here. So this is the time, but the y axis is the traffic density or velocity along the route 1, 3, 3, 4. So let's see how the density and velocity evolves along this route. So the red means the higher value. And this is the how mean-field game control the work. So I want to draw your attention to this peak here. This is actually when the two traffic streams coming from node 1 and 2 meet at node 3. So you can see on the LWR control, they all meet at the same time at node 3. That's why they incur high density and accordingly low speed. But in mean-field game setting, you don't see that because cars coming from node 2 would anticipate that if they drive at a faster speed, they may encounter a lot more cars at node 3. So that's why they intentionally slow down before they reach node 3. So that these two streams will not meet at the node 3 at the same time. So again, this tells us fast is slow if we can design the objective function or reward properly. So any questions for the network setting? Okay, so then I may move on to the mixed traffic. So if assume we have both the autonomous vehicle controlled by mean-field game and also the human-driven car follow some classical traffic flow model, how that works. We have to introduce the traffic density for both populations and velocity also for both populations. So for the flow equation, which is the conservation law, it's the same, but for AV and HV accordingly. And their sum is the total population density rho. And for the dynamic equation for mean-field game, we have a HJP equation. It's a little complicated, but actually in general, we try to solve this optimal value based on optimal control U. And also for the ERZ model, it's another second order traffic flow model. They have so-called momentum equation, where H here is the hesitation function to describe how cars react when given this current density. So you can see that for the human driven car, they react to the total population density. But for AV, they are able to communicate, so they can identify, not only they can sense the total population density, but also the density of the human-driven cars. And then I will directly show you what's the result findings here. So we compute the state stability regime for the mixed traffic condition. And the x-axis is the penetration rate for AVs, and the y-axis is the total normalized total density between 0 and 1. So you can see the blue dot means this area is traffic is stable. But for the crosses mean this in this regime, when the traffic fall within this regime, it's unstable. I will show you some animation to demonstrate how this makes a difference. So we will assume the total density is 0.4, and then there's no AV. So AV penetration rate is 0 on this chart. So then it ends up with this non-stable regime. And then we also, in parallel, we compare when we introduce 30% of AV, because in this regime, the traffic is stable. So we can see in the animation how the traffic density evolves in time and space. You can see when there's an AV, no AV, so the traffic density jump and a shock forms. But when there's 30% of AV, actually, the traffic evolves very smoothly. So that shows that in mean-field game, if AV is controlled by mean-field game, and if we design the objective function properly, it can automatically also mitigate the traffic's instability. So this can also inform how we can better design an autonomous controller based on the stability regime. And so, yeah, now I will move on to the algorithm, how we solve the mean-field game. The classical method, including solving a variational form, it basically reformulate mean-field game as a potential game. And then the most common one is a fixed point iteration. Basically, you solve the forward and backward partial differential equation iteratively until it converge. But there's also the shortcoming that it may fail to converge if the planning horizon is too large. And there's also Newton method basically convert the whole 2 PDE system into a big equation and solve that. The most recent trend is to use learning method to solve mean-field games. And now I will mainly focus on how we use learning methods. So first, let me introduce how normal people use fixed point iteration to solve it. So we start with the initial density and also velocity, use U0 and rho 0. And then remember we have these two partial differential equation, one FPK, one is HJB. So then we can solve the U and the rho iteratively. So basically, first solve the HJB, then we end up with the U, and then we solve FPK and end up with rho. So then we just iterate these two equations solving until it converges. Hopefully, it converges to an optimal solution. And we propose instead an online policy learning algorithm. So basically, when the car is driving along the way, we collect the samples. And then based on sample, we can update the algorithm to solve the optimal policy and also the value function. So assume this car is trying to explore this circular road, and we have initial gas Q. Here is a Q value function. And rho 0 is the initial density. And then when this car drives a little small stretch, and it can collect its reward, assuming there's some simulator that can give feedback on reward. And then this car keep driving and collect more sample and can update the Q value and also the rho value. And so basically, this algorithm, every time we collect small sample, we can update the value function and also the traffic density. And turns out we show that this algorithm can converge faster, and also it can converge to the basically the gradient we saw from this method is the right gradient that will converge to this optimal policy. So because of the time limit, I will skip the detail, but if you are interested, you can refer to the 3 papers we have published in this area. So you may ask another question, given there are already existing methods that model human, the autonomous vehicle and also mixed traffic, why do we still need a mean-field game approach? So I believe this mean-field game can actually augment the traffic flow model if we can come up with these different objective functions, because objective function is very easy to manipulate. And we also already established equivalence with the between the condition classical traffic flow model and the mean-field game, including LWR and generic second-order model like ARZ model. They are actually a special mean-field game if we design the reward function properly. If we come up with some other cost function, so that we can come up with more mean-field game that may lead to new traffic flow patterns. However, in this space, there are some other concerns that if the objective function is not properly designed, it can lead to physically inconsistent outcome. For example, the car may drive backwards. That's why we need to be careful when we try to design new objective function that can also follow some or observe traffic laws or physical traffic rules. And this is when physics-informed domain knowledge can help. And before I wrap up my talk, I want to also present some challenges and the future work that I believe could be promising for control of autonomous driving. Is the causality. For the why causality, let me show you a quick video clip. So this is a video uploaded by some Twitter user to their account. When they are driving on the highway, trying to merge to the highway, the car dash cam actually captured a Waymo car in front with the left turning lights blinker on. Basically, Waymo car also tried to merge to the mainland highway, but failed eventually. It had to get off to the next off-ramp. Given all the surrounding human drivers were able to do so. So there are many reasons this Waymo car failed, but I want to interpret it from this perspective of causality. And so assume we train this Waymo car using imitation learning. We provide some expert trajectories for, say, thousands of human trajectories when they try to merge to mainland highway. And then when we present this trajectory, the self-driving car will interpret, okay, I observe some action that human drivers trying to steer their wheel to left and have the left turning blinker on. I observed that they were able to make lane change. So given this observation, I assume I can also do the same thing using some learning algorithm. However, what they are missing is there are some unobserved confounder in the environment. In this case, it's the surrounding driver's behavior. Their behavior are latent. We cannot collect their data into the learning data sets. But their behavior significant impact whether this learn change can be accomplished or not. So causality can actually help the learning algorithm to be more powerful and then capture accounting for these unobserved confounder when they try to train a self-driving car to learn. So for more detail, you can also refer to our 3 papers listed here. I would like to thank my students, my postdoc, and also my collaborators. So that's it. Thank you.